Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind, and knowledge becomes a soft lullaby for the night. Tonight's journey drifts toward a question that has whispered through science fiction, late-night conversations, and the edges of serious physics for more than a century. Faster than light travel. Not as a race or a spectacle, but as a calm exploration of why the universe seems to allow such ideas on paper, while gently but firmly refusing to let them exist in reality. Before you settle in completely, I'll offer a small invitation. If you enjoy these slow, curiosity-driven wanderings through science, you're always welcome to like the video or subscribe, only if it feels right to you. And if you're still awake enough to type, you might leave a comment sharing where in the world you're listening from and what time it is for you right now. It's a quiet comfort to imagine minds scattered across the planet, each in their own pocket of night, all listening together. Now, feel free to dim the lights, adjust your pillow, or let a soft background sound settle in. There's no need to concentrate too hard. If your thoughts drift, that's perfectly fine. This is not a lecture to keep up with, but a story to float through. We'll move slowly, translating the language of physics into images and feelings that are easier to rest with. And as we go, you may find that the universe's strictest limits are not barriers at all, but the gentle structures that make existence stable, predictable, and safe enough to sleep beneath. When you're ready, let's begin. Before we ever talk about stars, engines, or distant galaxies, it helps to notice a small, almost invisible assumption most of us carry through life. We tend to believe that speed is simply a matter of effort and improvement. If something is slow, we imagine making it faster. Better roads, stronger engines, lighter materials. History seems to support this idea. We once travelled on foot, then by horse, then by steam and steel, and eventually by machines that lift us cleanly off the ground. Each step feels like a promise that the next barrier will also fall. So when we hear about the vast distances between stars, it feels natural to think in the same way. Surely, we tell ourselves, the problem is just that our technology isn't good enough yet. We picture future ships, brighter engines, cleverer designs. In that picture, the universe is wide but negotiable, and speed is just another challenge waiting to be solved. This assumption is so quiet that we rarely question it. It sits beneath our thoughts like a smooth floor, supporting everything we imagine about travel and progress. But physics has a habit of gently tapping on such assumptions and asking whether they truly belong there. To see why, imagine walking through a long hallway. At first, each step takes you forward in a predictable way. Walk faster and you reach the end sooner. Now imagine that hallway slowly turning into soft sand. With each step, pushing harder doesn't help as much as you expect. The ground itself resists. Eventually, no matter how much effort you apply, your speed barely changes. At that point, the problem is no longer your legs or your shoes. No, it's the nature of the ground beneath you. In our universe, speed behaves a bit like that hallway. Up to a point, going faster is exactly what it seems. More energy, more motion, more distance covered. But as you approach a certain ultimate pace, the one we often call the speed of light, something subtle shifts. Space and time themselves begin to change how they respond. Clocks tick differently. Distances behave strangely. Effort no longer translates into progress in the way intuition expects. What's important here is that this ultimate speed is not really about light at all. Light simply happens to move at this pace because it has no weight and no rest. The deeper truth is that this speed appears to be a structural feature of reality itself. It is the rate at which cause and effect can unfold. The universe seems to have a built-in rhythm. a maximum tempo at which information, influence and change can travel. When we assume that faster than light travel is just a technical hurdle, we are quietly assuming that this rhythm can be adjusted, that the universe's tempo is negotiable. Physics, however, keeps hinting that it is not. Think of reality as a vast, carefully synchronized performance. Every event cues the next. Every cause has room to become an effect. This synchronization depends on a shared limit, a universal agreement about how quickly one moment can influence another. Remove that agreement, and the choreography begins to unravel. Effects could arrive before causes. Messages could return before they were sent. The story of what happens first and what happens next would lose its meaning. None of this feels dramatic in everyday life because we live far below that ultimate pace. Our cars, planes, and even our fastest spacecraft move slowly compared to the universe's maximum rhythm. At these gentle speeds, space and time behave politely. They don't call attention to themselves. They let us believe that speed is simply a number on a dial. But the moment we start dreaming seriously about faster-than-light travel, we are no longer turning a dial. We are pressing on the very framework that holds time, order, and sequence together. The universe doesn't respond with anger or explosions. It responds with something quieter and more profound. It reshapes the rules themselves. In this calm realization lies the heart of our journey. Faster-than-light travel is not forbidden in the way a locked door forbids entry. It is constrained in the way a load-bearing wall constrains a building. You can imagine removing it. You can even draw plans that show empty space where it once stood. But if you actually try, everything above begins to sag, crack, and collapse. As this idea settles, there's no need to feel disappointed. Limits like this are not punishments. They are what allow the universe to be stable enough for atoms to form, for chemistry to unfold, and for minds like yours to lie quietly in the dark listening to stories about stars. Understanding this doesn't close a door. It opens a deeper kind of wonder, one that invites us to see speed not as a challenge to defeat, but as a clue to how reality quietly takes care of itself. It's easy to assume that the speed of light is simply the speed at which light happens to move. After all, the name seems to say exactly that. Light travels fast. We measured it. We gave the number a symbol. End of story. But this is one of those moments where a familiar phrase quietly hides a much deeper idea, and where physics asks us to slow down instead of rushing ahead. Imagine for a moment that tomorrow every light bulb on Earth stopped working. The sun still rose, stars still shone, and the universe carried on exactly as before. The laws of reality would not suddenly need rewriting just because visible light went dark. And yet the speed we call the speed of light would remain just as important as ever. That alone should hint that this speed is not really about brightness or beams or glowing things crossing space. A gentler way to think about it is this. The speed of light is the universe's speed limit for cause and effect. It is the fastest pace at which one event can influence another. It is how quickly reality itself can update. If that sounds abstract, picture an enormous digital display stretching across the cosmos. Every tiny square on that display needs to know what its neighbours are doing in order to stay consistent. If information travelled infinitely fast, the display could change anywhere, any time, without order. But if updates happen at a fixed maximum speed, patterns remain coherent, shapes hold together, stories make sense. In our universe, that update speed is what we call the speed of light. This is why light moves at that speed. Light carries information. It announces that something has happened. When a star flares or an atom vibrates, light is how the news spreads. But light is not special because it moves fast. It moves fast because it is bound to this deeper rule. Once you see it this way, the idea becomes almost comforting. The universe is not chaotic or impulsive. It has a rhythm, a tempo, a maximum pace at which reality can unfold without tearing itself apart. This rhythm shows up in places we don't usually notice. It shows up in the fact that there is such a thing as now, even if it is slightly different for observers moving differently. It shows up in the way causes come before effects. It shows up in the quiet reliability of sequence. First this, then that. When we imagine faster than light travel, we are not just imagining a faster ship. We're imagining stepping outside that rhythm. We're imagining a message arriving before it was sent, or an effect occurring before its cause has had time to exist. Even if that sounds like clever storytelling, the universe treats it as a serious structural problem. To understand why, it helps to think of the speed of light as the width of the universe's threads. Spacetime, the fabric of reality, is woven from relationships between events. Each thread can only stretch so far, so fast without snapping. That limit is not arbitrary. It is what keeps the fabric from unraveling. This is also why scientists don't describe the speed of light as something technology will eventually overcome. You can't engineer your way past the thickness of a thread by pulling harder. You can only tear it. There's another quiet clue hidden in everyday technology. Satellites that help your phone find its location must account for the fact that time itself ticks differently when moving fast or sitting in weaker gravity. Engineers don't do this because it's philosophically interesting. They do it because if they don't, the system fails. Your map drifts, your directions break down. Even at speeds far below light speed, space-time already insists on being respected. That insistence grows stronger the closer you get to the universe's maximum pace. Space contracts, time stretches, cause and effect begin to lean toward their limits. These are not warnings posted on a sign. They are physical responses built into the structure of reality. So when science fiction imagines faster than light travel as a simple extension of speed, physics gently shakes its head. It's not that the idea is rebellious or imaginative, it's that it misunderstands what the speed of light represents. This speed is not a hurdle at the end of a long technological race. It is more like the frame of the racetrack itself. You can run faster or slower within it. But if you try to step outside the frame, there's nothing left to run on. Seen this way, the speed of light becomes less of a limitation and more of a quiet organizer. It keeps events in order. It prevents the future from leaking backward into the past. It ensures that information arrives in time to make sense. And this brings us to an important shift in perspective. Faster than light travel doesn't fail because we lack cleverness. It fails because cleverness alone cannot renegotiate the structure that allows reality to remain coherent. As you rest with this idea, there's no need to hold on to every detail. The feeling is enough. The universe has a pace, a shared rhythm that everything agrees to follow. Light simply dances at the edge of that rhythm, tracing its outline so we can see where it lies. Understanding this doesn't make the universe feel smaller. It makes it feel carefully built, thoughtful, stable enough to host galaxies, chemistry, life, and quiet moments like this one, where nothing needs to happen faster than it already does. There is a quiet structure beneath everything that happens, something so steady that we rarely notice it unless it is threatened. It is the simple idea that causes come before effects. You strike a match, and then it lights. You speak, and then the sound arrives. This ordering feels so obvious that it almost disappears from thought, and yet, physics treats it as one of the most delicate and carefully protected features of reality. To understand how the universe maintains this order, it helps to imagine not objects, but events. A clap of thunder, a leaf falling, a star exploding. Each of these is an event, happening at a particular place and time. Now imagine drawing faint lines outward from each event, spreading in all directions, marking where its influence can reach as time passes. These lines do not spread instantly. They move outward at the universe's maximum pace, the same pace we associate with the light. This creates a gentle boundary around every event. Inside that boundary, influence is possible. Outside it, nothing has yet arrived. It is not a wall you can see, but a limit that quietly shapes what can affect what. Physicists often picture this boundary as a kind of cone extending into the future, widening as time goes on. But you don't need to picture cones or diagrams to feel the idea. You already live inside it. When you look up at the night sky, you're seeing stars as they were long ago, not as they are now. Their light has taken time to reach you. Their influence is still on its way. In that delay lies the proof that the universe does not allow instant connections across space. It insists on patience. This patience is what keeps cause and effect aligned. If influence could travel faster than this universal pace, something strange would happen. Two observers moving differently through space might disagree on the order of events. One could say the cause came first. Another could insist the effect arrived earlier. The simple story of this led to that would fracture into contradictions. The universe avoids this not by negotiation, but by structure. It arranges space-time so that the order of events remains consistent for everyone, no matter how they move. This consistency is not a convenience. It is the backbone of meaning. Without it, prediction fails. Memory becomes unreliable. Planning loses its footing. To see how fragile this order is, imagine reading a book where the pages occasionally rearrange themselves. A character reacts before anything has happened. Consequences appear without causes. You might tolerate it for a few pages, but soon the story becomes impossible to follow. Reality works the same way. Without a stable sequence, it cannot tell a coherent story. This is why faster-than-light ideas cause such deep concern in physics. They are not merely about moving quickly. They threaten to scramble the sequence that reality depends on. A message sent faster than the universe's allowed pace could arrive before it was sent, at least according to some observers. The past and future would blur. The notion of before and after would lose its universal meaning. It's tempting to think this is just a philosophical problem, something that clever logic or careful rules might fix. But the universe doesn't treat it that lightly. It responds with physical resistance. Whenever a theory allows influences to outrun this cosmic pace, it tends to produce instabilities, paradoxes, or conditions that cannot sustain themselves. You can think of the universe as a careful editor, trimming away stories that cannot be told consistently. Any plotline that allows effects to precede causes is quietly removed, not by decree, but by deeper laws that make such situations collapse under their own contradictions. What makes this even more remarkable is that the universe enforces this order locally, everywhere, all the time. There is no central clock keeping score. Each region of space follows the same rule, respecting the same maximum pace for influence. This shared agreement is what allows distant parts of the universe to fit together into a single, comprehensible whole. As we move closer to the idea of warp drives and faster-than-light motion, it becomes important to keep this picture in mind. The problem is not speed itself. The problem is sequence. Any method that tries to bypass the universe's pacing risks tearing the threads that hold cause and effect together. And yet, this protection is not harsh or aggressive. It is gentle. It shows up as limits that grow stronger the more you press against them. Time stretches, energy demands rise, control slips away. Each response is a quiet reminder that reality is built to preserve order, not to maximize convenience. In everyday life, this order is a gift. It allows learning, it allows trust, it allows the simple comfort of knowing that tomorrow follows today, not the other way around. In the vastness of the cosmos, the same principle scales up, guiding galaxies and stars through a shared rhythm. So when we speak about faster than light travel, we're really speaking about whether this rhythm can be broken without shattering the song. Physics suggests that it cannot. The universe is not being stubborn, it is being consistent. As this idea settles, you might notice how calming it is. There is something reassuring about living in a reality that takes cause and effect seriously. That does not rush. That does not allow the future to leak backward into the past. It means that even in a universe full of mysteries, there is a quiet reliability at its core. And with that reliability comes rest. Because when cause and effect remain in order, the world remains predictable enough to inhabit and stable enough to dream within. The speed of light, seen this way, is not a barrier in the dark. It is a soft boundary drawn to keep the story of the universe readable from beginning to end. There is a moment, deep in the mathematics of motion, where speed stops being just speed and begins to change the nature of time itself. It is not a dramatic moment. There is no sudden flash or warning. Instead, it arrives quietly, almost politely, as you move faster and faster through space, asking you to reconsider what time really is. In everyday life, time feels steady. Seconds pass one after another with reassuring regularity. A minute feels like a minute whether you're sitting still or walking down the street. This reliability encourages the belief that time is something universal, something everyone shares equally. But physics gently reveals that this comfort is an approximation, one that only holds when speeds are low and gravity is mild. As motion becomes more extreme, time begins to behave differently. Imagine carrying a clock with you on a long journey. Not a special clock, just something simple and familiar. And now imagine that you begin moving faster and faster relative to someone who stays behind. From your perspective, nothing feels unusual. Your heart beats normally. Your thoughts flow at their usual pace. The clock ticks calmly, just as it always has. But from the perspective of the observer you left behind, something subtle has changed. Your clock is ticking more slowly than theirs. Not because it is broken, and not because it is poorly made, but because motion itself has altered the way time flows for you. This effect is often called time dilation, though the phrase can sound more technical than it needs to be. A gentler way to think about it is this: motion through space reshapes motion through time. The faster you move one way, the less freely you can move the other. A helpful image is to picture a fixed amount of motion that must be shared. At low speeds, almost all of that motion goes into moving through time. But as speed through space increases, some of that motion is redirected. Time slows, not out of choice, but out of necessity. The universe seems to insist that the total motion always balances. This is not a trick of perception. It is not about clocks malfunctioning or observers being confused. It is built into the structure of space-time itself. Experiments have confirmed it repeatedly, using particles, precision clocks, and satellites orbiting Earth. Whenever motion increases, time responds. What matters for our journey is what happens as speed approaches the universe's maximum pace. As you move closer and closer to that limit, time dilation becomes stronger and stronger. So to an outside observer, your clock slows more and more. From their perspective, your journey stretches out. Reaching the limit would require time itself to stop completely for you relative to them. And that is where the quiet impossibility reveals itself. Reaching the maximum pace would mean that time, as measured by the rest of the universe, would no longer flow for you at all. Every process would freeze. Motion through time would halt. The universe does not allow objects with mass to enter that state. Instead, it responds by demanding more and more energy for smaller and smaller increases in speed. This is not a punishment. It is a consequence of how space-time is shaped. You can think of it like trying to tilt a heavy object on a table. At first, a small push makes a noticeable difference. Push harder and it tilts further. But as you approach the point where it would topple, the resistance grows sharply. The object does not smoothly pass into the next state. It resists with increasing insistence. Time behaves the same way. The closer you get to the ultimate speed, the more stubborn time becomes. This stretching of time has a curious emotional effect when you imagine it. From your own perspective, the journey could feel perfectly ordinary. You might cross vast distances while aging very little. Meanwhile, the universe outside races ahead. Stars evolve. Civilizations rise and fall. What feels like a brief trip to you could span centuries elsewhere. This idea has inspired many stories, and it often sounds like a clever loophole. Travel far, return young, outsmart time itself. But notice what is actually happening. You're not defeating the universe's pace. You're obeying it so strictly that time rearranges itself around you to maintain consistency. And consistency is the key word. Time dilation exists to preserve the order of cause and effect. By slowing time for fast-moving objects, the universe ensures that signals, influences, and interactions remain well behaved. Nothing sneaks ahead of the rhythm. Nothing jumps the cue of causality. As speed increases, the universe does not open new doors. It closes them more carefully. This brings us closer to understanding why faster-than-light travel is not simply an extension of time dilation. You cannot stretch time just a little more and slip past the limit. The closer you approach, the more time itself resists being reshaped. This resistance is not mechanical. It is structural. It comes from the way space-time connects motion, energy, and sequence into a single fabric. Pull too hard on one thread, and the others tighten in response. For listening minds drifting towards sleep, there is something oddly comforting about this behavior. Time is not fragile. It does not shatter under pressure. It flexes, adapts, and protects the coherence of reality. It ensures that experiences remain ordered, that memories make sense, and that the universe does not dissolve into contradiction. As we move forward in this journey, we'll see how some ideas attempt to avoid this resistance by not moving through space at all, but by reshaping space itself. Those ideas are mathematically elegant and deeply imaginative, but the stretching of time you've just encountered will remain in the background, quietly reminding us that the universe guards its rhythm with patience and care. For now, it's enough to rest with the image of time as something alive, responsive, and protective. Not a rigid ticking machine, but a flowing dimension that adjusts itself to keep the story of the universe readable. And in that steadiness, there is room to relax. Because when time stretches instead of breaking, the world remains a place where events follow one another gently, and where sleep can arrive without fear of the future rushing in too soon. As time stretches under increasing speed, another change quietly unfolds alongside it. This change is less poetic at first glance, but just as important. It has to do with energy, and with how stubborn the universe becomes when you try to push something closer and closer to its ultimate pace. In everyday experience, energy feels straightforward. Push harder, go faster, add more fuel, travel farther. If something resists, we assume the solution is simple: apply more effort. This intuition works well for bicycles, cars, and even rockets, but it begins to fail in a very particular way as speed climbs toward the universe's maximum rhythm. Imagine pushing a cart across a smooth floor. At first, each extra bit of effort produces a noticeable increase in speed. The cart responds politely. Now imagine that, as the cart moves faster, the floor beneath it slowly turns sticky. Each push still helps, but not as much as before. Push harder, and the gain becomes smaller. Eventually, no matter how much strength you apply, the cart barely accelerates at all. This is close to what happens when objects with mass are pushed toward the cosmic speed limit. As speed increases, Adding energy does not simply make the object move faster. Instead, the energy begins to sink into the structure of space-time itself. Motion becomes harder to change. Acceleration grows more reluctant. The universe responds as if it is absorbing your effort, redistributing it in ways that preserve its internal balance. Physicists often describe this by saying that the energy required to keep accelerating grows without bound. That phrase can sound abstract, so it helps to soften it into an image. Think of climbing a hill that becomes steeper the higher you go. At first, the incline is gentle, then it sharpens. Near the top, each step demands far more effort than the last. The summit never quite arrives. It keeps retreating upward no matter how much strength you summon. In this picture, the hilltop represents the maximum speed of the universe. You can approach it endlessly, but you can never stand on it. What's remarkable is that this behavior is not added by hand. It is not a rule someone decided to enforce. It falls naturally out of how space-time relates energy, motion, and time. The closer you get to the limit, the more energy is required for smaller and smaller gains. Eventually, the amount of energy needed becomes so large that the concept itself loses practical meaning. This is where faster-than-light travel as traditionally imagined quietly breaks down. To cross the limit by pushing harder would require an infinite supply of energy, not a very large amount, not an unimaginably large amount, an unending amount. The universe simply does not provide such a resource. Again, this is not a moral judgment or a technological challenge waiting to be solved. It is a statement about structure. The universe is not built to support infinite accumulation in this way. There is also a deeper reason for this resistance. Energy is not just fuel. It shapes space-time. As energy increases, it changes the geometry through which motion occurs. The more you pour in, the more space-time responds by altering distances and durations in ways that counter further acceleration. It is a kind of self-regulating behavior. You can think of it as a feedback system. Push harder, and the system stiffens. The universe does not allow runaway motion that would destabilize its internal order. At this point in the story, many imaginative minds look for a clever escape. If pushing an object faster and faster fails, perhaps the solution is not to push the object at all. Perhaps the road itself can be moved. Perhaps space can be shaped so that the destination comes closer instead of the traveller moving faster. This thought does not come from science fiction alone. It arises naturally once you realise that space-time is flexible. It bends under energy and mass. It stretches and compresses. If energy shapes space, maybe space can be shaped in useful ways. Before we follow that idea further, it's worth pausing to appreciate what this energy barrier really tells us. The universe is not indifferent to effort. It responds proportionally, but only up to a point. Beyond that, it begins to protect itself. It redirects energy into maintaining coherence instead of allowing unchecked motion. This behavior ensures that no object with mass can outrun the causal structure that keeps events ordered. In simpler terms, energy grows without end because it has to. If it did not, the universe would allow objects to reach and surpass the maximum pace, unravelling the careful sequencing of cause and effect we explored earlier. The infinite energy requirement is not an inconvenience, it is a safeguard. From a quiet human perspective, there is something grounding about this. No matter how ambitious a journey might be, it cannot demand more than the universe is willing to give. There is a balance between motion and meaning that cannot be bypassed by force alone. As listeners, you don't need to hold on to the image of infinite energy too tightly. What matters is the feeling it conveys. Yeah, the closer you press against the universe's deepest limits, the more it resists. Not abruptly, but gradually, patiently, and completely. This resistance sets the stage for one of the most intriguing ideas in modern physics. If pushing through space fails, And if energy refuses to cooperate, perhaps the only remaining option is not to move faster, but to move differently, to let space-time itself do the travelling. That idea will soon appear not as fantasy, but as a legitimate solution written directly into the equations that describe gravity and motion. For now, it's enough to rest with the realization that energy, like time, stretches and stiffens to preserve order. The universe does not slam doors shut. It simply makes them heavier the closer you try to force them open. And in that steady resistance, there is again a sense of calm. A reminder that reality has limits not to frustrate us, but to remain whole. Energy grows without end because it must, and because without that growth, the story of the universe could not remain coherent enough to tell. After watching time stretch and energy grow heavier with every attempt to go faster, a different kind of idea begins to feel almost inevitable. If pushing an object through space meets such firm resistance, perhaps the mistake is trying to move the object at all. Perhaps the universe is hinting that motion itself needs to be reimagined. To feel this shift, imagine standing on one of those moving walkways in an airport. You're not running, you're barely walking at all, and yet the floor beneath your feet carries you forward faster than you could comfortably move on your own. From your perspective, nothing feels extreme. Your body stays relaxed. Your pace remains gentle. Still, the distance behind you grows quickly. In this simple image lies the seed of a profound idea. What if long journeys through the cosmos could work the same way? What if a spacecraft didn't need to race through space, straining against time and energy, but could instead rest calmly while space itself flowed around it? This thought is not a metaphor invented for comfort. It emerges naturally from the way gravity works in modern physics. Gravity, as we understand it, is not a force pulling objects through space like an invisible hand. It is the way space and time bend, stretch, and curve in response to energy and mass. Objects follow the paths that this curved space-time lays out for them. If space-time can bend, then in principle it can be shaped. It can be compressed in one region and expanded in another. Distances can shrink here and grow there, all without any object locally breaking the universe's speed limit. This is an important point to rest with. The universe does allow space itself to change at rates that appear faster than light. We see this most clearly in the expansion of the cosmos. Very distant galaxies are carried away from us as space stretches between us and them. Their separation grows faster than light could cross the gap, yet no galaxy is actually racing through space at an impossible speed. The road is lengthening, not the cars accelerating. So the idea of reshaping space is not speculative. It is something the universe already does on vast scales. From this perspective, faster than light travel begins to look less like rebellion and more like clever alignment. You're not asking an object to outrun causality. You're asking space-time to rearrange itself so that the destination comes closer. This is where imagination and mathematics meet. Physicists have found that the equations describing space-time do not forbid such rearrangements. In fact, they quietly permit solutions in which space contracts in front of a region and expands behind it. Inside that region, everything remains calm. Clocks tick normally, objects are at rest relative to their immediate surroundings, and yet the region as a whole can move across vast distances at an effective pace that exceeds light speed. It is a subtle distinction, but a crucial one. Nothing inside the region ever moves faster than the universe allows. Locally, all the rules are obeyed. It is only when you compare distant points that the journey seems impossibly fast. This approach feels almost polite. Instead of forcing your way through the universe, you ask the universe to rearrange itself gently around you. For a moment, this idea feels like a breakthrough. It sidesteps the infinite energy barrier. It avoids the freezing of time. It respects the local speed limit everywhere along the way. It seems to honour the letter of the universe's laws while slipping past their spirit. This is why the concept has captured so much attention. It feels like a loophole that the universe accidentally left open. But before excitement carries us too far, it helps to pause and notice something subtle. The universe does not distinguish between moving an object and moving the structure that defines motion. From its point of view, both are changes to space-time. Both must fit within the same deep constraints that preserve order and stability. The moving walkway analogy works beautifully at human scales, but it hides an important detail. Someone had to build the walkway. Someone had to supply the energy to keep it running. Someone had to manage the forces that keep it stable and safe. When the walkway becomes space-time itself, those hidden requirements become enormous. To compress space in front of a region and expand it behind, you must reshape space-time's geometry in a very specific way. This shaping is not free. It requires energy, and not just any kind of energy. It demands patterns of energy that behave very differently from the familiar kinds we encounter in everyday life. At this stage, the idea of warp travel is still only a whisper. Like it is a suggestion written into the language of geometry rather than engineering. But it is enough to shift the entire conversation. Faster than light travel no longer depends on pushing harder. It depends on sculpting reality itself, and this is where the story begins to deepen. Because once you allow space-time to become dynamic in this way, you're no longer dealing with speed alone. You're dealing with the fabric that connects events, carries causality, and supports the existence of matter and time. Every attempt to reshape it must contend with the universe's insistence on coherence. For now, it's enough to let the image settle. A calm region of space carried gently across the cosmos by the motion of space itself. No rushing, no straining, just a quiet glide over immense distances. It is a beautiful idea, elegant, almost serene. And like many beautiful ideas in physics, it invites a closer look. Not to dismiss it, but to understand what the universe quietly demands in return for such grace. As your thoughts slow, you can hold on to that image of the moving walkway through space, a reminder that sometimes the most powerful shifts come not from force, but from changing the ground beneath our feet. Once the idea of moving space instead of the traveller has settled into the mind, something remarkable begins to happen. The problem of faster-than-light travel no longer feels like a clash with the universe. It starts to feel like a question of permission. Not technological permission, but mathematical permission. And mathematics, it turns out, can be surprisingly generous. At the heart of modern gravity lies a set of equations that describe how space-time bends and responds to energy. These equations do not describe motion directly, they describe shape. They tell space and time how to curve, stretch and fold, and then allow matter and light to follow the paths created by that geometry. What's important here is not the equations themselves, but their character. They do not dictate a single rigid universe. Instead, they allow a vast family of possible space-time shapes, each internally consistent, each obeying the same underlying rules. Some of these shapes look familiar, like the gentle curvature around planets and stars. Others are far more exotic, bending and twisting space-time in ways that feel almost imaginative. This openness is not a flaw, it is a feature. The equations are designed to describe relationships, not to police which shapes are allowed to exist. As long as a space-time configuration satisfies the mathematical relationships, it is considered valid, at least on paper. This is where a quiet door opens. When physicists explored these equations with creativity and care, they discovered that nothing in the mathematics forbids a space-time geometry where space is compressed in front of a region and expanded behind it. Inside that region, everything can remain calm and ordinary. Outside, space-time itself does the moving. In other words, the equations allow a kind of wave of space, carrying a bubble along with it. This discovery was not framed as a proposal for a spaceship in the traditional sense. It was presented as a solution to the equations, a demonstration that such a geometry could exist mathematically. No engines were specified, no materials were listed. It was simply a proof of concept written in the language of geometry, and that is why it caused such a stir. For the first time, faster-than-light travel seemed to emerge not from fantasy, but from the same mathematical framework that successfully describes black holes, gravitational waves, and the expansion of the universe. It felt like finding a hidden corridor in a building you thought you knew well. But mathematics has a peculiar kind of honesty. It will show you what is logically allowed without guaranteeing that it can be built, sustained, or even approached in the real universe. It is generous with possibilities but silent about practicality. A helpful way to think about this is to imagine drawing a bridge across a canyon. On paper you can sketch elegant arches, sweeping curves and graceful spans. The drawing may be perfectly consistent. Every line connects, every angle makes sense, but the drawing does not tell you whether steel can bear the load, whether the wind will tear it apart, or whether the ground can support its weight. Mathematics gives permission to draw. Physics decides whether the drawing can stand. This distinction is subtle but essential. The equations of space-time allow many geometries that the universe never realizes. Some would require conditions that cannot form naturally. Others would collapse the moment they appear. Still others would demand resources or arrangements that contradict deeper physical principles. The idea of a warp-like geometry belongs squarely in this category. It is mathematically sound, internally consistent, and surprisingly elegant. But elegance on paper does not guarantee survival in reality. There is also something quietly important about how these solutions are found. They are static snapshots, descriptions of what space-time could look like if it already existed in that shape. They do not explain how to create such a shape, how to maintain it, or how to control it. They simply say, if space-time were arranged this way, the equations would not object. This is not a minor omission. In physics, the difference between existing and being creatable is enormous. Many configurations are mathematically allowed but physically unreachable. They are like perfect still-life paintings of structures that could never be assembled from the materials of the real world. And yet, the existence of these solutions is not meaningless. On the contrary, they act like mirrors. They reflect the underlying structure of the theory back at us, revealing what it values and what it protects. By allowing such geometries mathematically, the equations invite us to ask deeper questions. Why does the universe permit these shapes on paper but resist them in practice? What additional rules come into play when energy, stability, and causality are considered together? These questions turn faster-than-light travel from a technological fantasy into a diagnostic tool. Warp-like solutions become probes, testing the boundaries between mathematics and reality. There is something calming in this realization. The universe is not teasing us with forbidden toys. It's offering insights into its own architecture. It is showing us that the laws we use to describe gravity are flexible, imaginative, and rich, but also that they are part of a larger system of constraints that work together to keep reality coherent. So when we say that mathematics allows faster-than-light geometries, we're not saying that the universe is careless. We're saying that mathematics is exploratory. It maps the full space of logical possibilities, even those that reality ultimately declines to inhabit. As this idea settles, it helps to let go of the urge to turn every mathematical permission into a promise. Some doors open not to let us pass through, but to let us see how the room is built. And in the quiet space between permission and possibility, as a deeper understanding begins to form, one that prepares us for the next layer of the story, where the universe gently explains what it requires in exchange for bending space-time in such dramatic ways. For now, it's enough to rest with the thought that faster-than-light travel first appears not as a machine, but as a shape, a geometry allowed by equations, waiting patiently to be tested by the realities of energy, stability, and time. When the mathematics of space-time quietly opened the door to faster-than-light geometries, one particular idea stepped into the light with unusual clarity. It did not arrive as a blueprint for a spacecraft, or as a promise of future engineering. It arrived as a carefully shaped thought, written in the language of curved space and time. This idea is often called the warp bubble, and it provides one of the clearest illustrations of how faster-than-light motion can appear without anything locally breaking the universe's speed limit. To picture a warp bubble, it helps to return to a calm, everyday image. Imagine floating on a gentle river. You're not swimming, you're not straining. The water carries you along. From your point of view, you remain still relative to the water around you, even though the shoreline slips past at a steady pace. Your motion comes not from effort, but from the flow of the medium itself. The warp bubble is built on the same intuition. Inside the bubble, everything is quiet and ordinary. The spacecraft does not accelerate in the usual sense. People inside would feel weightless, calm and unhurried. Clocks tick normally. No one is pressed back into their seat. Nothing locally rushes or strains. All the action happens in the space around the bubble. In front of the bubble, space is gently squeezed. Distances shorten. The destination is brought closer without anyone needing to move toward it. Behind the bubble, space stretches, lengthening the distance already travelled. The bubble itself rides this pattern of compression and expansion, carried forward by the geometry of space-time. From the outside, the bubble appears to cross enormous distances in a very short amount of time. The effective speed can exceed that of light, sometimes by a great deal. But this speed is a kind of illusion created by reshaping distance, not by outrunning the universe's pace locally. This distinction is subtle, but it is the reason the idea fits within the equations of gravity. At every point inside the bubble, the familiar rule holds. Nothing moves faster than light relative to its immediate surroundings. The universe's local speed limit remains untouched. For a moment, this feels like a perfect solution. The infinite energy barrier no longer applies in the same way because the spacecraft is not being pushed through space. Time dilation does not freeze the crew because they are not racing toward the limit. Causality, at least locally, seems intact. This is why the warp bubble captured so much attention. It feels respectful, almost courteous. It follows the rules while sidestepping their most frustrating consequences. But there is an important detail hidden beneath this elegance. The warp bubble is not a thing that moves through space-time, it is a configuration of space-time itself. And configurations like this come with requirements that are easy to overlook when focusing only on motion. To create the bubble, space-time must be bent in a very specific pattern. Space must compress in one region and expand in another, with a sharp boundary between the calm interior and the active exterior. This boundary is not just a line, it is a region where space-time changes rapidly, and rapid changes always demand energy. Not just any energy either. The equations reveal that to sustain this pattern, the energy involved must behave in an unusual way. In some regions, it must effectively pull instead of push. It must reduce energy density rather than increase it. This is what physicists often describe as negative energy, though the phrase can sound more dramatic than it needs to be. A softer way to think about it is this. Normally, energy weighs space-time down, curving it inward. The warp bubble requires space-time to curve outward in certain places. That outward curvature demands an energy pattern that is opposite to what we usually encounter. This requirement does not make the warp bubble mathematically illegal, but it does make it physically demanding in a very specific and troubling way. Another detail often missed in casual discussions is control. The warp bubble, as described mathematically, is a complete space-time arrangement. It does not include instructions for steering, braking, or adjusting course once it exists. The geometry simply is what it is. This means that, in its pure form, the warp bubble behaves less like a vehicle and more like a wave. It carries whatever is inside along a predetermined path. And the idea of a pilot adjusting controls does not naturally appear in the mathematics. Control would require additional structures layered on top of an already delicate configuration. Still, even with these caveats, the warp bubble remains one of the most illuminating ideas in modern physics. Not because it promises a future of interstellar travel, but because it exposes the difference between what is mathematically consistent and what the universe is willing to realize. It shows us that faster-than-light motion does not violate the equations of gravity by default. Instead, it runs into deeper issues related to energy, stability, and causality. The bubble itself is like a beautifully drawn sketch of a machine that cannot yet be built and may never be buildable, not because of missing tools, but because of how reality is structured. There is something almost poetic in this. The universe allows us to imagine such shapes, to write them down, to explore their consequences, and then it quietly asks whether we are prepared to meet the conditions they require. As you sit with this image, try not to see the warp bubble as a failed dream. See it as a lens. It magnifies the rules that keep space-time coherent. It reveals how carefully the universe balances flexibility with restraint. Inside the bubble, calm reigns. Outside, space-time does the work. And at the boundary between the two, the universe draws a line, reminding us that reshaping reality comes at a cost that cannot be ignored. This understanding prepares us for the next step in the story. Because once the warp bubble is clearly seen, the question naturally shifts. If the equations allow it, but reality resists it, what exactly is the universe protecting? And why does every attempt to make such a bubble real seem to awaken deeper and deeper constraints? Those questions are waiting patiently, just beyond the edge of this elegant geometry. After the elegance of the warp bubble settles in, a quiet question begins to surface. If the equations allow such a geometry, if nothing locally breaks the universe's speed limit, and if time and energy seem, at least at first glance, to cooperate, then why does this idea remain so firmly out of reach? The answer lies in a subtle but crucial distinction, one that mathematics itself does not enforce, but reality does. There is a difference between something being internally consistent on paper and something being physically realizable in the universe we inhabit. To feel this difference, imagine drawing a perfect circle on a page. Every point lies exactly where it should. The shape is flawless. Now imagine trying to draw that same circle in sand at the beach. The grains shift, the edges blur. Tiny imperfections appear no matter how careful you are. The concept of the circle remains valid, but the medium refuses to cooperate fully. Mathematics works like the paper. It describes relationships with infinite precision. Physics works like the sand. It deals with materials, energy, noise, and imperfections that cannot be erased. Warp drive geometries belong to this gap. The equations of space-time describe what shapes are allowed if space-time could be arranged however we like. They do not tell us whether the universe provides the tools, materials, or conditions needed to assemble those shapes. They simply say, if space-time looked like this, the equations would still hold. This is why warp solutions are often described as exact solutions. They are complete descriptions of a space-time configuration, not instructions for creating one. They tell us what the finished structure would look like, not how to build it step by step. This difference matters deeply. In the real universe, nothing appears fully formed. Structures emerge from processes. Stars ignite from collapsing clouds. Planets form from disks of dust. Even black holes grow through accumulation and collapse. The universe is procedural. It builds through history. Warp geometries, in contrast, often appear as if they must exist all at once. There is no smooth path from ordinary spacetime to a fully formed warp bubble without passing through regions of extreme distortion. During that transition, energy densities spike, instabilities grow, and the gentle assumptions of the equations begin to break down. In other words, even if the final shape is mathematically calm, the act of creating it may be violently unstable. This brings us to a deeper layer of resistance. Reality does not just care about what exists, it cares about how things come into existence. The universe seems to enforce what might be called constructibility. If a configuration cannot be assembled from physically allowed processes, it remains a mathematical curiosity rather than a physical possibility. This is not unique to warp drives. There are many solutions in physics that describe exotic situations which cannot arise naturally or be engineered. They exist in the landscape of equations like distant mountain peaks, beautiful, precise, and unreachable. Another way to think about this is to imagine a frozen lake. On paper, you can draw a path straight across the ice. The line is perfect. But whether you can actually walk that path depends on the thickness of the ice, the temperature, and the cracks hidden beneath the surface. The drawing does not warn you where the ice will fail. Reality does. Warp geometries are similar. They appear smooth and controlled in mathematical descriptions. But when you ask how they would behave in a universe filled with quantum fluctuations, gravitational ripples, and imperfect energy distributions, the picture begins to fray. There is also the matter of scale. Many warp solutions require space-time to be shaped sharply over very small distances. Such sharp gradients amplify every tiny disturbance. What looks stable in a perfectly clean equation becomes unstable in a universe that is never perfectly still. Quantum effects in particular refuse to stay quiet. Even empty space is alive with fluctuations. Energy briefly appears and disappears. Fields vibrate. These effects are usually gentle and average out. But near extreme space-time geometries, they can grow dramatically, feeding on the very distortions required to sustain a warp bubble. This means that the more aggressively you try to reshape space-time, the more loudly the quantum nature of reality pushes back. There is something revealing in this response. The universe does not merely block faster than light travel at one point. It resists it at every level. Geometry, energy, causality, and quantum behavior all align in quiet agreement. Each individual rule seems reasonable on its own. Together, they form a web of constraints that is remarkably difficult to slip through. And this is where the deeper lesson begins to emerge. The universe does not operate like a list of permissions and prohibitions. It operates like an ecosystem. Change one element too aggressively, and others react. Push geometry, and energy responds. Push energy, and quantum effects amplify. Push causality, and stability collapses. Warp drive mathematics reveals this interconnectedness with unusual clarity. It shows that faster-than-light motion is not forbidden by a single law, but by the combined insistence of many. For a listening mind drifting toward rest, there is something almost reassuring about this. Reality is not fragile. It does not shatter because of a clever equation. It protects its coherence through layers of mutual support. So when we say that warp drives are allowed on paper but resisted in practice, we are not describing a failure of imagination. We are describing a success of structure. The universe is consistent with itself, even when our ideas stretch toward its edges. As we move forward, the story will deepen further. The resistance we've touched here is only the beginning. Beneath it lie more specific constraints, ones tied to unusual forms of energy, to horizons that block control, and to instabilities that grow the harder we try to tame them. For now, it's enough to hold on to this quiet distinction. Mathematics explores what could be. Reality decides what can endure. And between those two lies a space of understanding, where the universe reveals not only its limits, but the reasons those limits exist at all. At this point in our journey, the warp bubble no longer feels like a simple idea about motion. It has become a question about what the universe is willing to provide in exchange for reshaping reality itself. And this is where we encounter one of the strangest requirements in all of modern physics, something that sounds almost backwards when first described. To understand it gently, let's begin with something familiar. In everyday experience, energy pushes. Heat makes things expand. Pressure presses outward. Mass weighs space-time down, pulling it inward like a heavy object placed on a soft mattress. This behavior is so universal that it feels almost like a definition of energy itself. Energy fills, presses, supports, and stabilizes. The warp bubble, however, instead asks for something different. In order to compress space in front of the bubble and stretch it behind, space-time must curve outward in certain regions, not inward. It must behave as if something is lifting the fabric of reality rather than weighing it down. The equations describing this geometry quietly insist on a form of energy that does the opposite of what energy usually does. Instead of pushing, it pulls. Instead of adding weight, it removes it. This is what physicists often refer to as negative energy. The phrase can sound alarming, as if it implies something fictional or dangerous. But a softer way to think about it is this. Negative energy describes regions where space-time behaves as though there is less energy than the surrounding vacuum would normally contain. Even empty space, as strange as it sounds, is not truly empty. It hums with activity. Fields fluctuate. Energy briefly appears and fades. This restless background sets a kind of baseline. Negative energy means dipping below that baseline, creating a pocket where space-time feels lighter than usual. The universe does allow such pockets to exist, but only in very quiet, fleeting ways. One of the most famous examples comes from a subtle laboratory effect involving two closely spaced surfaces. When they are brought extremely near each other, the background energy of empty space changes slightly between them. The effect is tiny, delicate, and difficult to measure. It is often described as a whisper rather than a shout, a small rearrangement of the vacuum's restless energy. This phenomenon is important not because it enables warp drives, but because it proves something crucial. Yeah, negative energy is not forbidden outright. It exists, but it exists in a very constrained form. The scale of this effect is the key. The negative energy produced in such experiments is unimaginably small. It flickers into existence for brief moments over microscopic distances. It is not something you can gather, store, or amplify freely. It does not behave like fuel waiting to be refined. The warp bubble, by contrast, demands negative energy on a colossal scale. Not a trace, not a whisper, but a sustained, structured pattern strong enough to reshape space-time over distances large enough to hold a spacecraft and carry it across the stars. This is not a matter of missing technology. It is a matter of mismatch. The universe offers negative energy like dew on a spider's web, delicate, transient, and sparse. The warp bubble asks for an ocean. What makes this requirement especially revealing is that it does not arise from engineering limitations. It comes directly from geometry. The shape of space-time demanded by the warp bubble simply cannot be supported by ordinary, positive energy alone. No amount of familiar matter or radiation will curve space in the required outward direction. This means that even before questions of control, stability, or safety arise, the universe places a fundamental condition on the table. If you wish to bend space-time in this way, you must supply an ingredient that reality provides only reluctantly and in vanishingly small amounts. There is something almost polite about this refusal. The universe does not slam the door. It leaves it slightly ajar, showing that the concept is not logically impossible. But it also makes clear that stepping through would require resources that do not naturally accumulate. This is where many hopeful discussions pause. The thought arises that perhaps future technology will find a way. Perhaps negative energy could be generated more efficiently. Perhaps the tiny whispers observed in laboratories are just the beginning of a louder conversation. But here, it helps to remember the pattern we've seen before. When the universe allows something only in small, fleeting doses, it is often because larger doses would disrupt deeper balances. The scarcity is not accidental, it is protective. Negative energy in this sense is not a fuel the universe forgot to make abundant. It is a carefully rationed exception, allowed just enough to reveal the structure of quantum space, but not enough to rewrite space-time on demand. As you sit with this idea, it may begin to feel less like a disappointment and more like a clue. The universe is not teasing us with forbidden ingredients. It is showing us where its priorities lie: stability, coherence, order. The warp bubble's requirement for negative energy is the first clear signal that bending reality at this scale comes with costs that cannot be negotiated away. It tells us that faster-than-light motion is not merely about clever geometry. It is about whether the universe is willing to lend us the very substance that holds space-time together, and so far it lends only the smallest amounts, briefly and with great care. This realization gently prepares us for the next layer of resistance. Because even when negative energy appears, it does not appear freely. Yes, war. It comes with conditions, constraints, and obligations, like a loan that must be repaid quickly and with interest. For now, it is enough to rest with the image of those quiet whispers in empty space, fleeting pockets where energy dips just below its usual hum, proof that the universe can bend in subtle ways, but also proof that it guards its deeper structures closely. The warp bubble is not rejected outright. It is asked a question instead. Where will you find what you require, and what are you prepared to give back in return? At this point in our journey, the warp bubble no longer feels like a simple idea about motion. It has become a question about what the universe is willing to provide in exchange for reshaping reality itself. And this is where we encounter one of the strangest requirements in all of modern physics, something that sounds almost backwards when first described. To understand it gently, let's begin with something familiar. In everyday experience, energy pushes. Heat makes things expand. Pressure presses outward. Mass weighs space-time down, pulling it inward like a heavy object placed on a soft mattress. This behavior is so universal that it feels almost like a definition of energy itself. Energy fills, presses, supports, and stabilizes. The warp bubble, however, asks for something different. In order to compress space in front of the bubble and stretch it behind, space-time must curve outward in certain regions, not inward. It must behave as if something is lifting the fabric of reality rather than weighing it down. The equations describing this geometry quietly insist on a form of energy that does the opposite of what energy usually does. Instead of pushing, it pulls. Instead of adding weight, it removes it. This is what physicists often refer to as negative energy. The phrase can sound alarming, as if it implies something fictional or dangerous. But a softer way to think about it is this. Negative energy describes regions where space-time behaves as though there is less energy than the surrounding vacuum would normally contain. Even empty space, as strange as it sounds, is not truly empty. It hums with activity. Fields fluctuate. Energy briefly appears and fades. This restless background sets a kind of baseline. Negative energy means dipping below that baseline, creating a pocket where space-time feels lighter than usual. The universe does allow such pockets to exist, but only in very quiet, fleeting ways. One of the most famous examples comes from a subtle laboratory effect involving two closely spaced surfaces. When they're brought extremely near each other, the background energy of empty space changes slightly between them. The effect is tiny, delicate, and difficult to measure. It is often described as a whisper rather than a shout, a small rearrangement of the vacuum's restless energy. This phenomenon is important not because it enables warp drives, but because it proves something crucial. Negative energy is not forbidden outright. It exists, but it exists in a very constrained form. The scale of this effect is the key. The negative energy produced in such experiments is unimaginably small. It flickers into existence for brief moments, you see over microscopic distances. It is not something you can gather, store, or amplify freely. It does not behave like fuel waiting to be refined. The warp bubble, by contrast, demands negative energy on a colossal scale. Not a trace, not a whisper, but a sustained, structured pattern strong enough to reshape space-time over distances large enough to hold a spacecraft and carry it across the stars. This is not a matter of missing technology. It is a matter of mismatch. The universe offers negative energy like dew on a spider's web, delicate, transient, and sparse. The warp bubble asks for an ocean. What makes this requirement especially revealing is that it does not arise from engineering limitations. It comes directly from geometry. The shape of space-time demanded by the warp bubble simply cannot be supported by ordinary positive energy alone. No amount of familiar matter or radiation will curve space in the required outward direction. This means that even before questions of control, stability, or safety arise, the universe places a fundamental condition on the table. If you wish to bend space-time in this way, you must supply an ingredient that reality provides only reluctantly and in vanishingly small amounts. There is something almost polite about this refusal. The universe does not slam the door. It leaves it slightly ajar, showing that the concept is not logically impossible. But it also makes clear that stepping through would require resources that do not naturally accumulate. This is where many hopeful discussions pause. The thought arises that perhaps future technology will find a way. Perhaps negative energy could be generated more efficiently. Perhaps the tiny whispers observed in laboratories are just the beginning of a louder conversation. But here, it helps to remember the pattern we've seen before. When the universe allows something only in small, fleeting doses, it is often because larger doses would disrupt deeper balances. The scarcity is not accidental. It is protective. Negative energy, in this sense, is not a fuel the universe forgot to make abundant. It is a carefully rationed exception, allowed just enough to reveal the structure of quantum space, but not enough to rewrite space-time on demand. As you sit with this idea, it may begin to feel less like a disappointment and more like a clue. The universe is not teasing us with forbidden ingredients. It is showing us where its priorities lie: stability, coherence, order. The warp bubble's requirement for negative energy is the first clear signal that bending reality at this scale comes with costs that cannot be negotiated away. It tells us that faster-than-light motion is not merely about clever geometry. It is about whether the universe is willing to lend us the very substance that holds space-time together. And so far, it lends only the smallest amounts briefly and with great care. This realization gently prepares us for the next layer of resistance, because even when negative energy appears, it does not appear freely. It comes with conditions, constraints, and obligations, like a loan that must be repaid quickly and with interest. For now, it is enough to rest with the image of those quiet whispers in empty space, fleeting pockets where energy dips just below its usual hum. Proof that the universe can bend in subtle ways, but also proof that it guards its deeper structures closely. The warp bubble is not rejected outright. It is asked a question instead. Where will you find what you require, and what are you prepared to give back in return? Once the idea of negative energy is settled, another realization follows naturally, almost quietly. Even when the universe allows something unusual to exist, it rarely does so without conditions. There is a sense, woven deep into physical law, that nothing is given freely for long. This is where the story shifts from what the universe allows to how it keeps track. A helpful way to approach this is to think of the universe as an exceptionally careful accountant. Not a strict one with a loud voice or harsh penalties, but a patient one who notices every imbalance and gently corrects it over time. Whenever something dips below the usual baseline, something else must rise to compensate. Whenever energy behaves strangely in one place, it must behave more forcefully somewhere else. Negative energy, as rare and delicate as it is, does not escape this bookkeeping. In the quiet laboratory effects that hint at negative energy, the universe allows a small imbalance to appear. But it does so briefly, and within tight boundaries. The moment that imbalance grows too large or lasts too long, it is countered. Positive energy appears nearby. The background fluctuations rearrange themselves. The overall balance is restored. Physicists describe this behavior using what are often called quantum limits, but the name matters less than the idea. The universe permits borrowing, but only on very short terms and always with repayment. A gentle metaphor helps here. Imagine dipping a cup into a calm lake and lifting it out. For a moment, the water level in that spot is lower than the surrounding surface, but almost immediately water flows back in. The dip cannot persist. The lake refuses to stay uneven. Negative energy behaves in much the same way. You can create a small dip, but the surrounding universe responds quickly. The deeper the dip, the faster and stronger the response. This has profound consequences for warp travel. The warp bubble does not ask for a brief dip. It asks for a sustained valley. It needs regions of negative energy that persist long enough and strongly enough to hold space-time in an unnatural shape as it moves across cosmic distances. From the universe's perspective, this is not a small loan. It is a massive overdraft, and the universe responds accordingly. The rules that govern negative energy insist that any region where energy drops below its usual baseline must be balanced by regions where energy rises above it. Not later, not elsewhere, but closely in time and space. The larger and longer the negative region, the larger and more immediate the compensation must be. This means that even if you could somehow assemble the required negative energy for a warp bubble, the surrounding space-time would react violently to restore balance. Positive energy would surge, fields would fluctuate more intensely. The very structure you are trying to hold in place would be undermined by the universe's effort to settle its accounts. It is important to notice what this is not saying. The universe is not forbidding negative energy outright. It is not declaring warp drives illegal. Instead, it is saying that large, stable imbalances are incompatible with the way quantum reality behaves. This is why appeals to future technology fall flat here. Technology can improve efficiency, it can refine control, it can reduce waste, but it cannot change the universe's accounting rules. No matter how advanced a civilization becomes, it cannot convince reality to ignore its own balance sheet. This is often where hopeful speculation gently fades, not because imagination runs out, but because the constraints are not technological in nature. They are structural. They arise from the way quantum fields behave even in the emptiest regions of space. Another way to feel this is to imagine trying to hold a vacuum open underwater. You can create a small pocket of air for a moment, but water rushes in from all sides. To maintain the pocket, you must constantly push against the surrounding pressure. The larger the pocket, the harder the water pushes back. Eventually, the effort becomes overwhelming. Negative energy pockets face a similar pressure, not from water, but from the restless activity of quantum space. The universe does not tolerate large regions of imbalance quietly. It smooths them out. This smoothing behavior has a calming implication. It suggests that the universe is deeply invested in stability. It does not allow extreme conditions to linger unchecked. It does not let small irregularities cascade into global chaos. From this perspective, the scarcity of usable negative energy is not a disappointment, it is a feature. It prevents space-time from being twisted into shapes that would threaten causality, coherence, and order. As listeners, you don't need to hold on to every detail of this cosmic bookkeeping. The feeling is enough. Whenever reality allows something strange, it does so cautiously. Whenever it lends energy in an unusual form, it expects repayment quickly and with interest. This is why warp drives encounter resistance not just once, but repeatedly. Geometry asks for negative energy. Quantum behavior limits how much negative energy can exist, and the universe's accounting system ensures that any attempt to stretch those limits is swiftly corrected. The door does not slam shut. It simply grows heavier the more you try to hold it open. As we drift onward, this idea will merge with another, equally important one. Yet even if energy constraints could be satisfied, space-time itself has preferences about how it bends and flows. Some shapes are naturally supported, others are resisted not by rules, but by the geometry of reality itself. For now, it is enough to rest with the image of a universe that keeps careful accounts, one that allows brief departures from the ordinary, but always guides itself back toward balance. In that steady bookkeeping lies the quiet reason why faster-than-light dreams remain dreams, and why the cosmos remains a place stable enough to host stars, planets, and nights of gentle rest. Up to this point, the universe has responded to warp ideas through energy. First by asking for something rare and unusual, and then by insisting that even that rarity must be tightly balanced. But beneath these energetic concerns lies something even quieter and more fundamental. It has nothing to do with fuel or fields or borrowing from the vacuum. It has to do with the way space itself prefers to behave. To approach this gently, let's begin without names or equations. Imagine releasing a handful of light rays into open space. They spread outward naturally, like ripples on a pond. Now imagine placing a heavy object nearby. The light no longer spreads as freely. Its paths begin to bend inward, drawn together by the presence of mass and energy. This is not because the light is being pulled in the usual sense, but because the space it moves through has changed shape. This behavior reveals something subtle about the universe. Space does not treat all motion equally. It has preferences. Certain patterns of movement are encouraged, and others are resisted. Objects and light tend to follow what might be called the easiest paths available to them. These paths are not straight lines in the ordinary sense, but natural routes determined by the shape of space-time itself. When space curves inward, these paths gently converge. When space flattens, they run parallel. This tendency is not optional. It is how geometry works. Positive energy, the kind we encounter in matter, radiation, and heat, always curves space-time inward. It acts like weight placed on a stretched fabric. The more weight you add, the more surrounding paths lean toward it. Light rays, particles, even the flow of time itself respond by bending and focusing. This inward focusing is not a side effect. It is a defining feature of how geometry and energy interact. Now consider what a warp bubble asks space to do. In front of the bubble, space must curve outward. Paths that would normally converge must spread apart. Distances must be defocused rather than focused. Space must behave as if weight has been removed, not added. From a geometric point of view, this is deeply unnatural. It is not forbidden in the abstract. You can write down shapes where paths spread instead of converge. But to maintain such shapes, something must actively counter the natural inward pull created by positive energy. Without that counterbalance, geometry snaps back to its preferred behaviour. This is why negative energy appears in the warp discussion so persistently. It is not an arbitrary requirement. It is the only known way to make space curve outward rather than inward. Without it, the geometry needed for a warp bubble collapses. What makes this particularly revealing is that this resistance comes from geometry itself, not from an added rule. Space is not being told what to do. It is doing what it naturally does when filled with ordinary energy. You can think of it like trying to make water flow uphill without a pump. The laws of fluid motion do not forbid uphill flow, but without constant intervention, water will always seek lower ground. Geometry behaves in a similar way. Without continuous, unusual support, space-time relaxes back toward inward curvature. Even more quietly, geometry resists sharp changes. The more abruptly you try to bend space, the more strongly it responds. Sudden transitions amplify stresses. Gentle curves are tolerated. Extreme shaping is not. Warp bubbles demand sharp boundaries. Inside the bubble, space-time must be calm and nearly flat. Outside, it must be highly distorted. The transition between these regions is where geometry protests most strongly. It is where stresses concentrate, and where stability becomes hardest to maintain. This means that even if energy constraints were somehow satisfied, geometry would still push back. Paths would try to converge, distortions would try to smooth out, the bubble would strain to relax into a less extreme shape. This behaviour is not hostile, it is restorative. Geometry is constantly trying to minimize distortion, to distribute curvature smoothly, to avoid sharp edges. This tendency keeps the universe stable. It prevents small irregularities from growing uncontrollably. It ensures that space does not tear itself apart under the weight of uneven shaping. In the context of warp drives, this tendency becomes a formidable barrier. The very shape that enables effective faster-than-light motion is one that geometry itself finds difficult to sustain. As listeners, it may help to picture this resistance as elastic tension. Stretch a rubber sheet gently, and it accommodates the change. Stretch it sharply in one spot and it snaps back. The warp bubble is a sharp stretch in the fabric of reality, one that demands constant, precise counterforces to hold in place. This geometric resistance also connects back to the universe's concern for causality. Inward focusing of paths helps preserve the order of events. It keeps influences contained. Outward defocusing, if allowed to persist unchecked, could loosen that containment, opening the door to causal confusion. So geometry, energy, and causality align quietly here. They are not separate guardians, but different expressions of the same underlying structure. Each reinforces the others. By the time we reach this point in the story, a pattern should feel familiar. Every attempt to make warp travel easier by addressing one issue only reveals another layer of resistance beneath it. Remove the energy problem and geometry resists. Soften geometry and causality phrase. Calm causality and quantum fluctuations grow louder. This is not coincidence, it is coherence. The universe is built from interlocking principles, not isolated rules. Geometry pushes back because it must, in order to support everything else. As your thoughts slow, you can rest with the idea that space is not passive. It is active, responsive, and quietly opinionated about how it prefers to bend. It tolerates stars and planets. It allows black holes. It supports cosmic expansion, but it resists being sculpted into shapes that undermine its deeper balance. Warp bubbles are beautiful on paper because geometry can imagine them. They're difficult in reality because geometry, when filled with real energy, seeks gentler forms. And in that seeking lies the reason the universe feels stable enough to trust. Space pushes back not to block our dreams, but to preserve the delicate structure that allows those dreams to arise in the first place. By now, the warp bubble has been tested by energy, by quantum balance, and by geometry itself. Each layer revealed a quiet resistance, not loud or dramatic, but persistent. And yet, even if we imagine, just for a moment, that all of these challenges could be solved, another problem waits patiently beneath them. This one is not about what the universe allows, but about what it lets you control. To approach this gently, imagine walking through a dense morning fog. You can see a few steps ahead, but the world beyond that fades into softness. Sounds arrive muffled. Shapes lose their edges. You're not trapped exactly, but your ability to respond is limited. You cannot see obstacles until you are very close. You cannot signal easily to what lies beyond the haze. Now imagine that the fog is not around you, but built by you. That by stepping forward, you're also creating the very boundary that blocks your view. This is close to what happens with a warp bubble. In the mathematical description of a warp bubble, the region inside is calm and protected. Space there is nearly flat. Time flows normally. But surrounding that calm interior is a boundary where space-time changes sharply. This boundary is not just a geometric feature. It also acts as a kind of horizon, a limit beyond which signals cannot easily pass back inward. From inside the bubble, the frontal edge is unreachable by ordinary signals. Light, radio waves, and any form of influence are carried along with the space-time inside the bubble. They cannot race ahead to the front boundary and report back. In effect, the region that determines where the bubble is going lies beyond the crew's ability to influence it. This creates a deeply counterintuitive situation. The faster the bubble moves, the more isolated its interior becomes from its own leading edge. The very mechanism that enables effective faster-than-light motion also cuts off communication with the region that defines direction and speed. You can think of it like being sealed inside a train car whose engine is outside the car, beyond any window or control panel. The train moves, but you have no direct way to tell it to slow down, speed up, or change course. You are a passenger inside a self-contained pocket of motion. This is not a minor inconvenience. Control is not an optional feature of a vehicle. It is what turns motion into travel. Without control, you do not navigate. You are carried. In traditional spacecraft, steering works because signals can move through the craft and out into space faster than the craft itself moves. Commands reach the front. Adjustments can be made. Feedback loops keep motion stable. In a warp bubble, this hierarchy is reversed. The bubble's effective motion outruns the signals inside it. Information cannot propagate forward fast enough to influence the boundary that matters most. The bubble becomes causally disconnected from its own destination. This is why physicists sometimes describe warp bubbles as creating their own horizons. Not the dramatic kind associated with black holes, but a gentler, more subtle kind. A boundary where influence ends, not because of danger, but because of structure. The fog analogy returns here with more clarity. You're not blinded by accident. The fog is a consequence of how the environment is arranged. In the same way, the loss of control inside a warp bubble is not a design flaw. It is a natural outcome of how space-time is being reshaped. What makes this especially revealing is that it does not depend on energy shortages or instability. Even in a perfectly stable, perfectly supplied warp bubble, this control problem remains. It is baked into the geometry. This leads to a sobering realization. A warp bubble, as described by the equations, behaves less like a ship and more like a phenomenon. It is something that happens, not something that is piloted. You might imagine pre-programming the bubble, setting its path in advance like winding a clock and letting it run. But even then, the inability to respond to unexpected conditions becomes a serious limitation. The universe is not static. Gravitational waves pass through space, fields fluctuate, tiny disturbances accumulate. Without feedback, even a well-planned journey becomes fragile. There is also the question of stopping. If you cannot influence the front boundary, you cannot easily slow the bubble down. The very act of halting requires changes to the space-time configuration ahead of you. But that region lies beyond causal reach. Bringing the journey to a gentle end becomes as problematic as steering it. This is where the metaphor of sealed rooms becomes useful. Imagine being inside a room that is sliding across a floor pushed from the outside. You feel motion, but you cannot reach the walls that are doing the pushing. You cannot open a door to adjust the force. You are enclosed within the effect, not in command of it. For a universe that values causality, this arrangement is deeply telling. Control requires information flow. Information flow requires causal access. Your faster-than-light effective motion undermines that access by outrunning the signals that would normally maintain it. This is another example of the universe's quiet consistency. Every time we try to bypass one limit, another aspect of structure reasserts itself. Speed, energy, geometry, and control are not independent features. They are facets of the same underlying order. As listeners, it can be tempting to see this as yet another door closing. But there is a gentler interpretation. The universe is not rejecting the idea of warp travel outright. It is showing us what it means to move responsibly within space-time. Movement without control is not travel. It is drift. And drift, at cosmic scales, is not something the universe encourages lightly. As your thoughts slow, you might notice how this mirrors everyday experience. We are most comfortable when we can respond, adjust, and adapt. When events move faster than our ability to influence them, unease sets in. The universe seems to share this preference. It arranges itself so that motion and control remain aligned. In the warp bubble, that alignment breaks. The cost of outrunning the universe's rhythm is not just energy or stability. It is agency itself. This realization brings us closer to the heart of the matter. Even if warp drives could exist as stable structures, they would still struggle to function as vehicles in any meaningful sense. They would be marvels of geometry, but poor companions for travelers. And with that understanding, another layer of resistance comes into view. Because even phenomena that exist briefly and uncontrollably must still contend with the universe's deep intolerance for imbalance and instability. That story is waiting just ahead, carried on the quiet hum of fluctuations that never truly sleep. Even if we imagine a warp bubble that somehow satisfies the universe's demands for energy, geometry, and balance, and even if we set aside the problem of control, another challenge rises quietly into view. This one is subtle, almost easy to overlook, because it has nothing to do with rules being broken. It has to do with balance, and how fragile certain kinds of balance can be. To approach this gently, imagine balancing a pencil on its tip. For a brief moment, with careful hands and steady breath, it can stand. The pencil does not immediately fall. In theory, the position is perfectly valid. All the forces cancel out. Nothing forbids the pencil from remaining upright forever, but in practice it never does. The slightest vibration, the faintest breath of air, the tiniest unevenness in the surface sends it tipping over. The balance was real, but it was unstable. It existed only in a world without noise, disturbance, or time. The warp bubble lives in a similar kind of balance. On paper, the geometry can be arranged so that all the competing forces hold each other in check. Energy supports curvature. Curvature guides motion. Everything fits neatly into place. But this balance assumes a perfectly quiet universe, one without fluctuations, ripples, or imperfections. The real universe is not quiet. Even in the emptiest regions of space, there is a constant background hum. Quantum fields fluctuate. Tiny amounts of energy appear and disappear. Spacetime itself is gently stirred by distant events. Gravitational waves from merging stars pass silently through the cosmos. None of this is dramatic. None of it is violent, but none of it ever truly stops. For most structures in the universe, this background noise is harmless. Atoms, planets, and stars are built in ways that tolerate small disturbances. They wobble slightly, then settle back into stable arrangements. Their balances are forgiving. The warp bubble's balance is not. The geometry required for a warp bubble is extremely precise. Small deviations matter. A slight excess of energy here, a tiny shortfall there, and the delicate pattern begins to unravel. The boundary of the bubble shifts, distortions grow. The calm interior is no longer insulated from the chaos outside. Now, this is what physicists mean when they speak of instability, though the word can sound harsher than the reality it describes. Instability does not mean immediate destruction. It means sensitivity. It means that small disturbances are amplified instead of damped. Returning to the pencil, imagine that every tiny vibration of the table made the pencil lean a little more, rather than correcting itself. That is the kind of balance the warp bubble demands. What makes this especially challenging is that the disturbances cannot be eliminated. You cannot turn off the quantum hum of empty space. You cannot shield space-time from distant gravitational ripples. The universe is dynamic by nature, and any structure built within it must be able to tolerate that dynamism. The warp bubble, as currently understood, does not. Yet, the more extreme the bubble's motion, the more sensitive it becomes. Faster effective speeds require sharper space-time gradients. Sharper gradients amplify disturbances more strongly. What begins as a whisper becomes a noticeable sway. What begins as a sway becomes a collapse of the intended shape. This creates a troubling feedback loop. The very features that make warp travel appealing also make it fragile. Greater compression and expansion lead to greater instability. Stability, if it exists at all, appears to demand gentler shapes that no longer achieve dramatic effects. Once again, this resistance does not feel punitive. It feels protective. The universe seems to prefer structures that dissipate disturbances rather than magnify them. This preference is what allows galaxies to persist for billions of years, atoms to hold together, and planetary systems to remain orderly. It is a quiet bias toward calm. The warp bubble asks the universe to abandon that bias. It asks for a configuration that must remain perfectly balanced, while being continuously disturbed by an environment that never rests. From the universe's perspective, this is not a reasonable request. Another way to feel this is to imagine trying to keep a soap bubble perfectly spherical while walking through a gusty field. The bubble can exist, the shape is allowed, but the environment conspires, gently but relentlessly, to distort it. The more carefully you try to preserve its shape, the more sensitive it becomes to the slightest breeze. Quantum noise plays the role of that breeze at the smallest scales. It does not arrive as a single force, but as countless tiny fluctuations, each insignificant on its own, and together they form a constant background that any structure must accommodate. In stable systems, these fluctuations average out. In unstable ones, they accumulate. The warp bubble, balanced like a pencil on its tip, has no natural mechanism to absorb these disturbances. Instead, they grow, pushing the geometry away from its intended form. What happens next depends on the specifics, but the general outcome is clear. The bubble does not remain quietly intact. This insight adds another layer to our understanding. Faster-than-light geometries are not just hard to create, they are hard to keep. The universe allows many shapes in principle, but it favours those that can survive in a noisy, imperfect world. This preference is not written as a law. It emerges from the interplay of dynamics and structure. As listeners, there is something deeply human about this realization. Perfect balance is rare in life as well. We seek it, admire it, and sometimes glimpse it briefly. But enduring systems are those that can sway without falling, adapt without breaking. The warp bubble in its ideal form lacks that resilience. This does not mean that the idea is worthless. On the contrary, it teaches us something profound about the universe. Stability is not an afterthought. It is a central criterion for what can exist meaningfully over time. As your thoughts slow, you might notice how gently this lesson unfolds. The universe does not reject warp travel with a single dramatic prohibition. It allows the idea to stand just long enough for the smallest disturbance to reveal its fragility. And in that fragility lies a quiet message. Reality is built not for perfection, but for persistence. Not for flawless balance, but for balance that can endure a little noise. That endurance is what makes stars shine steadily, planets orbit reliably, and nights pass calmly enough for sleep to arrive. The warp bubble, beautiful as it is, asks for a stillness the universe does not possess. And so, like the pencil, it tips, not because it is forbidden, but because the world it inhabits is alive. Even if we imagine a warp bubble that briefly achieves balance, and even if it survives the quiet hum of fluctuations long enough to move, one final problem lingers in its path. This one does not hide in equations or subtle instabilities. It follows directly behind the bubble itself, like a shadow that grows longer the faster it travels. To approach this gently, imagine a snowplow moving through a deep winter road. The plow itself may glide smoothly, but the snow does not disappear. It piles up along the edges, building higher and heavier as the plow advances. The faster the plow moves, the more dramatic this accumulation becomes. What matters is not just the motion of the plow, but what happens to everything it pushes aside along the way. A warp bubble behaves in a similar fashion. As the bubble moves through space-time, it does not pass quietly through empty nothingness. Space is filled with particles, radiation, and subtle fields. Even in regions we call vacuum, there is activity. Photons drift. Particles wander. Fields fluctuate gently. All of these are normally harmless, forming the soft background of the universe. But when space-time itself is sharply reshaped, these quiet travellers no longer move freely. The front edge of a warp bubble acts like a collector. Particles and radiation that would normally pass through are swept up by the distorted geometry. They cannot easily enter the bubble, and they cannot slip around it in the usual way. Instead, they accumulate along the boundary, carried forward and compressed as the bubble advances. At first, this build-up is subtle. A few particles here, a bit of radiation there, nothing dramatic. But the longer the bubble travels and the faster it goes, the more pronounced the effect becomes. The snow keeps piling up. What makes this accumulation especially concerning is that energy grows as it is compressed. Particles trapped along the boundary gain energy simply by being confined and carried along. Radiation becomes more intense. The edge of the bubble begins to glow with stored potential, like a stretched spring waiting to be released. Inside the bubble, the journey remains calm. The crew feels nothing unusual. Clocks tick normally. Space feels serene. But just beyond the boundary, a dangerous imbalance is growing. This leads to a troubling question. What happens when the journey ends? When the warp bubble slows or collapses, the space-time geometry relaxes. The compressed region at the front no longer holds its shape. The accumulated particles and radiation are released all at once, no longer constrained by the warped geometry that held them in place. The result is not a gentle arrival. The stored energy surges forward, released in a concentrated wave. What was once a quiet build-up becomes an overwhelming burst. The destination region, which may have been calm and undisturbed moments before, is suddenly flooded with energy it didn't expect and cannot easily absorb. It is important to approach this without drama. This is not about explosions in the cinematic sense. It is about scale and concentration. Even a modest accumulation when released suddenly can overwhelm local structures. Radiation intensifies, particles collide with unusual force. The environment at the arrival point is radically altered. In effect, the warp bubble brings its own storm. This problem is not easily solved by shielding or clever design. The accumulation happens outside the bubble, in the very region that defines its motion. Shielding the interior does nothing to protect the destination. Slowing down gradually does not fully help either, because the geometry itself must unwind, releasing what it has gathered. Once again, the universe reveals a preference. It does not object to motion alone. It objects to motion that concentrates disturbances and then releases them abruptly. In ordinary travel, disturbances spread out. Exhaust disperses. Waves fade. The environment has time to respond. Warp motion reverses this logic. It gathers disturbances, carries them forward, and releases them suddenly. This behavior echoes what we have seen before. Every attempt to bypass one limit triggers another response. Control becomes difficult. Stability falters. And now, safety itself comes into question. The universe seems unwilling to allow journeys that leave destruction in their wake, even unintentionally. There is also a deeper implication here. The accumulation at the bubble's edge is not an accident of poor design. It follows naturally from how space-time guides motion. Sharp distortions redirect paths. Redirected paths concentrate energy. Concentrated energy demands release. This is not a flaw that can be patched. It is a consequence of the geometry itself. As listeners, you might notice how this mirrors familiar experiences. When pressure builds without release, it does not vanish quietly. When traffic bottlenecks form, congestion grows. When rivers are dammed, water rises. The warp bubble creates a bottleneck in space-time, and the universe responds as it always does. By this stage in the story, a pattern has become unmistakable. Faster-than-light motion does not fail for a single reason. It fails because it clashes with many quiet expectations the universe holds about how motion should behave. Motion should be gradual, disturbances should spread, and the energy should dissipate. Cause and effect should remain readable. Warp travel compresses, concentrates, and accelerates all of these processes, and in doing so, it creates consequences that cannot be easily undone. As your thoughts slow, there is something grounding in this realization. The universe is not hostile to travel. It allows motion on vast scales. It supports orbits, expansions, and gentle flows across billions of years. What it resists are shortcuts that gather imbalance and release it suddenly elsewhere. The dangerous wake of a warp bubble is not just a technical issue. It is another expression of the same protective logic we have seen all along. The universe prefers continuity over abruptness, balance over accumulation, and dispersal over concentration. This understanding brings us closer to the end of the journey. We're no longer asking whether warp drives are allowed. We're beginning to see why the universe arranges itself so that they are never comfortable, never safe, and never sustainable. And in that arrangement lies a quiet kindness. A cosmos that does not allow travellers to arrive by unleashing storms may be slower to cross, but it is far gentler to inhabit. By this point, the pattern should feel familiar. Each time the warp bubble seems close to viability, the universe responds with another quiet constraint. Energy is scarce, geometry resists, control slips away, instability grows, the wake becomes dangerous, and yet the human instinct is persistent. If one design fails, perhaps it can be refined. If one obstacle appears, perhaps it can be engineered around. This is where many newer warp proposals enter the conversation. They often begin with a hopeful tone. What if we reduce the need for negative energy? What if we soften the bubble's edges? What if we redesign the geometry so that the most extreme distortions are spread out more gently? On paper, these ideas look promising. The equations can be adjusted, the shapes can be smoothed. The most alarming requirements seem at first to relax, but each improvement carries a subtle cost. When negative energy is reduced, something else must compensate. Geometry still needs to curve outwards somewhere. If energy no longer provides that curvature, spacetime finds another way to express the imbalance. Often, that expression takes the form of deeper causal problems. The boundaries that once merely limited control begin to fracture the order of cause and effect more severely. In simpler terms, removing one support beam shifts the load to another. Some revised designs attempt to rely entirely on ordinary positive energy. They avoid exotic ingredients altogether, but in doing so they push spacetime into configurations where paths of influence can loop back on themselves. Effects can arrive before their causes. The universe reacts strongly to this, amplifying instabilities and making such configurations short-lived or unreachable. Other designs focus on reducing sharp boundaries, hoping to ease instability and prevent dangerous energy buildup. They spread the warp effect over larger regions, making the distortion gentler. This does improve stability in one sense, but it also weakens the effect itself. The bubble becomes less effective at shortening distances. The journey slows. The advantage of faster-than-light motion fades. This trade-off appears again and again. Strengthened stability and speed vanishes. Increased speed and stability collapses. The universe seems unwilling to offer both at once. There is also a deeper problem hidden beneath these revisions. Many improved designs still rely on idealized conditions. Perfect symmetry, perfect alignment, perfect isolation from noise. In the real universe, such perfection does not exist. Tiny irregularities always creep in, and as we have seen, warp geometries are unusually sensitive to those irregularities. This means that even designs that look stable in simplified models tend to fail when exposed to realistic conditions. Quantum fluctuations, gravitational ripples, and uneven energy distributions all conspire to push the geometry away from its intended shape. Each revision solves a problem locally, but worsens the global picture. This is why physicists sometimes describe the universe's response as a set of locked doors. Opening one does not grant passage, it simply reveals another barrier behind it. The structure is layered, not linear. Importantly, these doors are not locked out of spite. They are locked because the underlying architecture of reality demands it. Speed, causality, energy, and stability are not independent features. They support one another. Remove one constraint and the others become more rigid to compensate. This interconnectedness explains why appeals to advanced civilizations or future breakthroughs do not carry much weight here. The issue is not technological maturity. It is structural compatibility. No amount of cleverness can persuade spacetime to relax the very principles that allow it to remain coherent. Seen this way, the failure of improved warp designs is not disappointing, it is illuminating. Each attempt teaches us something new about the universe's priorities. It shows us which compromises are acceptable and which are not. It reveals that the speed of a light is protected not by a single rule, but by a network of mutually reinforcing constraints. As listeners, you might notice how this shifts the emotional tone of the story. Faster than light travel stops feeling like a dream that was crushed. It begins to feel like a mirror held up to reality, reflecting its deeper structure. The universe is flexible, but only within limits that preserve order. It allows creativity, but not at the expense of coherence. It tolerates bending, but not tearing. Improved warp designs fail not because we haven't tried hard enough, but because they push against a system that is already optimized for stability. As your thoughts drift, you can rest with this realization. Limits are not always walls. Sometimes they are frameworks that hold everything else together. The repeated failure of warp refinements is not a sign of closed-minded physics. It is a sign of a universe that knows how to protect itself. And that protection brings us to a final, central insight, one that reframes everything we have explored so far. The speed of light is not an arbitrary barrier placed in our path. It is a structural element, a support beam woven into the architecture of existence itself. That understanding waits quietly ahead and are ready to bring the entire journey into focus. By now, it should feel clear that the speed of light is not standing in our way by accident. It is not a speed limit in the way a sign on a road is a speed limit. It is something far more structural, woven quietly into the way reality holds itself together. To feel this, imagine an old building. At first glance, the walls look ordinary. They divide rooms, they hold up shelves, they seem replaceable. But hidden within the structure are load-bearing walls. Walls that are not just dividers but supports. Remove one and the ceiling sags. Remove another and cracks appear elsewhere. The building does not collapse immediately, but it begins to lose its integrity in ways that are difficult to predict or control. The speed of light functions like one of these load-bearing walls. It does more than limit how fast objects can move. It sets the pace at which cause and effect unfold. It determines how information spreads. It shapes how energy behaves, how particles interact, and how structures remain stable over time. When light speed appears in physics, it often does so quietly, embedded in relationships rather than announced as a rule. It links space and time together. It determines how electric and magnetic effects balance. It sets the scale at which mass and energy become interchangeable. These roles are easy to overlook because they feel natural. We grow up in a universe where they are already in place. But if you imagine removing or bypassing this limit, the consequences ripple outward quickly. If information could propagate arbitrarily fast, cause and effect would lose their reliable order, and signals could arrive before the events that created them. Feedback loops would break. Systems that rely on delay and response, like atoms settling into stable arrangements, would no longer behave predictably. Chemistry, for example, depends on the timing of interactions. Electrons respond to nuclei with a certain rhythm. Forces balance because responses are not instantaneous. If those responses could outrun the structure that governs them, bonds would not hold in the same way. Molecules would struggle to remain intact. On larger scales, gravity depends on the speed at which changes propagate. Orbits are stable because influences travel at a finite pace. Remove that pacing, and motion becomes erratic. Systems overshoot. Corrections arrive too late or too early. Stability gives way to oscillation and collapse. Even time itself is shaped by this limit. The way clocks tick, the way durations compare, and the way different observers agree on sequences of events all rely on a shared maximum speed for influence. This shared speed creates a common framework, allowing the universe to tell a coherent story about what happens when. Warp drives, by attempting to bypass this structure, threaten more than travel constraints. They tug at the threads that keep reality consistent with itself. This is why fixes become harder, not easier, as proposals grow more refined. The closer a design comes to true faster-than-light behaviour, the more strain it places on the load-bearing elements of spacetime. Energy imbalances worsen, causal puzzles deepen, instabilities multiply. The universe responds not because it is defending a rule, but because it is protecting a framework. Seen this way, the speed of light is not an obstacle imposed from outside. It is an internal support. It is part of what allows atoms to form, stars to shine steadily, and information to remain meaningful over time. There is a quiet elegance in this arrangement. Instead of many separate rules policing motion, a single structural element supports countless behaviours at once. Limit the speed of influence, and a vast range of stable phenomena become possible. As listeners, this can be a surprisingly comforting realization. The limits that frustrate our dreams of easy travel are the same limits that make existence dependable. They ensure that causes precede effects, that systems can settle, and that complexity does not unravel instantly. Imagine a universe without such supports. Everything could influence everything else immediately. No delay, no buffering, no gradual response. It would be a place of constant feedback, where small disturbances escalate without pause. Such a universe might be energetic, but it would not be livable. Our universe chose a different architecture. By setting a maximum pace, it allows room for structure. It gives systems time to respond. It permits balance to emerge. The speed of light is not a barrier at the edge of our reach. It is a beam holding the whole structure upright. Warp research, when seen through this lens, becomes something more than a failed engineering project. It becomes a way of probing which parts of reality are flexible and which are foundational. Each failed attempt marks the outline of a deeper support. As your thoughts slow, and you can rest with this image of a universe carefully built, not hastily assembled. A universe that does not race ahead of itself, but unfolds at a measured pace. The very slowness we sometimes lament is what allows memory, meaning, and continuity to exist at all. The speed of light holds the universe together not by force but by rhythm. And in that rhythm lies a final insight. Warp drives do not fail because we lack imagination. They fail because imagination has led us to the edge of structure itself, where the universe gently reminds us which walls cannot be removed without bringing everything else down. That realization prepares us for the final reflection, not on travel or speed or limits, but on what these limits quietly teach us about the nature of reality and about ourselves as beings who live comfortably within them.